Hey there, and welcome to The Explainer. Today, we're going to break down this really brilliant piece of engineering that you see on workhorse aircraft all over the world, the turboprop engine. You see them all the time, right? But how do they actually work? Well, it turns out it's a fascinating story of mixing two totally different types of technology. All right, let's jump in.
So to really get why the turboprop was even invented, you have to look at this performance gap it was built to solve. On one side of the coin, you've got your classic piston engines. Now, they are fantastic for takeoff and climbing. They give you a ton of power right away. But, they kind of run out of steam once you get up high or try to go too fast. Then on the other side, you've got the pure turbojet. It loves flying at high speeds and high altitudes. But its performance getting off the ground? Well, let's just say it can be a little sluggish.
So naturally, it makes you wonder, right? What if you could somehow take the raw, high-altitude power of a jet and fuse it with the incredible low-speed, high-thrust power of a propeller? Well, that is the exact question that led engineers to create the turboprop.
Okay, so to really understand how a turboprop works, we've got to look inside its core. And what's at its core? Basically, a jet engine. So let's peel back the layers and take a look at the heart of this machine, the gas turbine. Now, the key difference here is pretty wild. A piston engine, it has these separate little cycles, pop, pop, pop. But a gas turbine engine, it does everything. Intake, compression, combustion, exhaust, all at the same time in one continuous, powerful flow. So think of it less like a series of little explosions and more like a constant, controlled rush of power, a whoosh. So let's walk through that cycle. First, a whole bunch of air gets sucked into the intake. Then, a series of rotating blades, that's the compressor, squeezes that air down to an incredibly high pressure. That super compressed air then gets sprayed with fuel and lit on fire in the combustion chamber. And here's the magic part. The hot expanding gas blasts out the back, and on its way out, it spins a turbine wheel. That turbine is connected by a shaft all the way back to the compressor at the front, which keeps the whole thing going. It's a self-sustaining cycle once you get it started.
And here's a wild fact that just shows you how extreme the environment is inside these things. Only about 10% of all the air that gets pulled into the engine is actually used to burn fuel. So what's the other 90% for? Just cooling. The temperatures inside can hit 4,000 degrees Fahrenheit, so most of the air is just used to keep the whole thing from, melting.
So now we have this incredibly powerful gas turbine core. The big innovation of the turboprop was figuring out how to use that power to spin a big propeller out front. And as we're about to see, engineers came up with two very clever and very different ways to get that job done. And the benefits of this hybrid idea are just huge. You get the power and reliability of a jet engine, but you pair it with the amazing efficiency of a propeller, especially at speeds under, say, 400 miles per hour. And look at this. That propeller can give you 90% of the total thrust at sea level. That's why these planes just leap off the runway. They really find their happy place between 18,000 and 30,000 feet, which makes them incredibly versatile aircraft.
All right, let's break down the two main ways they're built. Over on the left, you have the fixed shaft engine. In this one, the propeller, the compressor, and the turbine are all locked together on one shaft. They spin as a single unit. But on the right, you've got the split shaft, or free turbine design. Here, the propeller gets its own separate turbine that is not physically connected to the main engine core. And believe it or not, this one single difference changes everything about how you fly the plane.
So, diving into the fixed shaft, the main thing to remember is it's all one piece. That means the engine runs at an almost constant speed the whole flight, usually somewhere between 96 and 100% RPM. So you might be asking, how does the pilot change power? Well, not by changing the engine speed, but by changing how much fuel is going in and by adjusting the angle or the pitch of the propeller blades. But here's the catch. If that engine fails, that windmilling propeller is now trying to turn the whole heavy compressor section, and that creates an absolutely massive amount of drag.
Now let's compare that to the split shaft. Here, the main engine part, they call it the gas generator, or N1, spins totally on its own, separate from the power turbine that spins the propeller. This gives the pilot a ton of flexibility. You can control the propeller speed and the engine speed independently. You can even feather the prop, basically stop it from spinning while the jet engine part is still running. So what's the trade-off? Well, there's this noticeable lag, a delay between when you push the power up and when you actually feel the thrust kick in.
Okay, so all this engineering theory is cool, but what does it actually mean for the pilot sitting up front? The answer is pretty much everything. These two designs create two completely different experiences in the cockpit.
And you can really see the difference right here with the cockpit controls. In a fixed shaft plane, the power lever is basically a fuel valve, but in a split shaft, that same lever controls the speed of the gas generator. And get this, in a lot of fixed shaft planes, there's no propeller lever at all. Even the condition lever does different things. And one, it sets the RPM, and the other, it's mainly just a fuel shutoff. It's really like learning two completely different languages to fly them. And the stakes when you're managing these engines are incredibly high. This quote from the FAA says it all. A turboprop pilot is constantly juggling limits. On a really cold day, you might be limited by torque. That's the twisting force on the propeller. But on a hot day, you could hit your temperature limit way before you ever get to max power. Go over either of those limits for just a few seconds, and you can literally destroy the engine from the inside out.
You know, the engine is actually most vulnerable during startup. There's a dreaded situation called a hot start, and it's when the temperature just skyrockets past its limits. This can happen if the battery's weak and can't spin the engine fast enough before the fuel starts flowing. The pilot has to be watching those gauges like a hawk, ready to slam the fuel cutoff instantly to prevent some really serious and really expensive damage.
Let's circle back to that power lag we mentioned in split-shaft engines. Here's what's actually going on. Almost all of the engine's useful thrust is made in just the last 30% of the gas generator's RPM range. So if you're below that, moving the power lever doesn't really do much. This means pilots have to learn to think way ahead, adding power much earlier than they would in a piston plane, especially when they're close to the ground.
And one of the absolute coolest features of a turboprop is something called the beta range. When you're on the ground, you can pull the power levers back past a gate, and suddenly you're not controlling fuel anymore. You are directly controlling the angle of the propeller blades. This lets you taxi with incredible precision. And if you pull it back even further, the blades go to a negative angle, and you get powerful reverse thrust to slow down. You can brake hard without ever touching the brakes. It's awesome.
So what's the big takeaway from all this? Well, the turboprop is an absolute marvel of power and efficiency, but all that power comes with a whole new level of responsibility for the pilot and command. So when you put it all together, what really makes this design so enduringly successful? You get this incredible power-to-weight ratio, you're very fuel efficient at those medium altitudes, your takeoff performance is just spectacular, you've got the amazing utility of reverse thrust, and at the end of the day, you have the incredible reliability of a turbine engine.
And this really is the bottom line. A turboprop airplane flies through the air just like any other plane. The wings work the same, the controls work the same. The real challenge for a pilot moving up to one of these isn't learning to fly the airplane. It's learning to master this incredibly complex, powerful, and demanding power plant.
And that right there is why the specialized training is so critical. Pilots have to become experts at this constant dance between torque and temperature. They have to learn to think ahead to manage power lag, to be hypervigilant during startup, and to handle the high-altitude environment. They aren't just learning a few new buttons, they are mastering an entirely new philosophy of power plant management.
The turboprop was such an ingenious hybrid, right? It blended old-school propeller tech with new-school gas turbine power, all to solve a very specific problem. It really makes you wonder, as we start looking towards electric and hydrogen power, what kind of clever combinations of old and new ideas are going to create that next huge leap in aviation? It's definitely something to think about. Thanks so much for joining us on The Explainer.